Hello. Okay, that one worked. 1 second. I know what's going on. Hold on. Would help to have everything started. All right, now let's try this. There we go. Test, test. All right. What we got here? All right, 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 all right. Okay, just give me a couple of minutes here. I am just trying to get something settled. Okay. Actually, why don't we just go ahead and swap out for Standen Pupper? Yeah, you. Let's load mini avatar, full pilot. There we go. There we go. That's probably a place. There we go. All right, now we're done. Now we're cooking with gas. Okay. Let's. Hello, and welcome to the first of many. I say as I try and do something. Hold on 1 second. Saturday morning papers. Yes, this is a new series that we're starting up. We're trying out. Okay. Let's get a test message in here, and it's popping up, and it's popping up, but it's not popping up there. Okay. We have a little bit of fixing to do. So I apologize for the scuff, as the kids call it. So shoot. Oh, I shouldn't have done that. Oh, I really shouldn't have done that. Oh, that was a bad idea. Uh-oh, Pascadios. Shoot. There we go. Okay. So why are you not then connected? WebSocket connected, it says. But the test message did not show. Then settings. So it says it's there, but it's not showing up on that. So I was trying to set up a visible chat here on this other computer that would. Don't worry about it. It's not a big deal. All right. We will figure that out another time, actually. Here. Does that show up here? It does not. Oh, okay. Uh, okay, so these are somehow not connected. message. Okay, you know what? We will close this for now. Hello? Hello? I don't get good with this, huh? Oh, yeah. Let's try disconnecting that again. Good. And now we want to go over to. Oh, awesome. Um. So somehow we managed to lock up a Linux machine. Yeah. All right. I'm gonna have to restart this. This guy over here. All right, this can't be manual restart. Cool. So, how's everyone going? How's it going, everyone? We're having fun. We're having fun, having a good time, having a good time. There we go. Having a good time, having a good time. Sorry. So how I have it set up right now, I've got my streaming box, and then I have a Linux machine that is. So that's good. A Linux machine on which I am running OneNote that I'm using to take notes for the paper. So I can show the paper and write. I have a little tablet that I can write on, all that stuff. But currently, the Linux computer is being a naughty computer. So I had to restart. So I apologize, but we'll be there in a second. Let's get into the. Unfortunately, of course, to make OneNote, the famously Microsoft program, function on Linux, I have to get Winboat working. So I have like several layers. I have a VM going on a Linux box, but we're getting there. All right. Let me just start up the OneNote here. There we are. All right. We got this. Beautiful. There we go. And hello. Welcome to the first weekly, theoretically, Sunday morning paper. The plan for this is to walk through a paper. This probably won't be too long of a stream, but just kind of walk through a paper, try to understand what's going on. These will be science papers of any sort that you would care to throw in there. Math papers, philosophy papers, literature, honestly, anything. And we'll do our best to understand it. I make no guarantees that we will be able to do so with 100% effectiveness, but we'll do our best. So, in honor of this being our first paper, we are actually going to go over one for those who are in the deep lore. We have done this before a long time ago, but that was when I first started streaming, like way back when. And so it's been a hot minute. Therefore, what we're going to do is we're going to go through this again. So this is about something called the Wigner distribution, and we will discover exactly what the Wigner distribution is. And I have evil plans to use this in the future. Regardless, I just kind of wanted to go over it again to refresh my memory, and I thought it would be a cool inaugural Sunday morning paper. So welcome, and let's get rolling. Okay. So, yeah. Let's just go direct. Let's hop into the introduction, shall we? Time frequency analysis is one of the most important areas of signal processing. The standard Fourier analysis, although very useful in identifying individual frequency components of a signal, has no time resolution. So, for those who don't know, right, the Fourier analysis breaks down any weird signal into a set of individual sines and cosines, right? So this plus dot, right? These all at different amplitudes. You add them all together and you'll get some other signal, right? So if you do that, what you're looking at is essentially, right? This is amplitude 1. This has amplitude 2, or again, amplitude is this, right? This has amplitude 3. This has amplitude 4. And if you were to go and plot this all, right, you would get like this. A 1 might be this tall. A 2 might be up here. A 3 might be over here. And a 4 might be here, right? And so you'd get some curve that looks kind of like this. And this would represent the Fourier transform of this, right? This is going to go, in theory, goes on and on forever, right? For anything other than an infinitely, other than an infinite oscillating signal, is going to actually have an infinite number of sines and cosines added up to compose it. But you'll notice our first signal here, right? This is time, this is amplitude, right? We've taken this and we've converted it to something that's, these are different frequencies, right? So this is amplitude, this is frequency, right? So what we've done is we've gone from amplitude versus time to amplitude versus frequency, which can be very useful, right? If I want, so let's say I'm worried about some kind of interference that's occurring at this point, I want to cut it out. I can actually cut out this frequency, right? And then reconstruct a version of the original by doing the inverse Fourier transform, but now without that frequency attached. So I can do all kinds of cool stuff with it. But again, as he said, once you've gone from here down to here, you no longer have time. This, right? Frequency, of course, is 1 over time. You've gone to a different variable. So that's what he's talking about. Standard Fourier analysis. Okay. Hence, efforts have continued in the last several decades to invent new methods for the analysis of local time and frequency content waveforms, right? Because the frequency content can change over time. Something can start at one frequency and change to a different frequency over a span of time. And so now your frequency content is going to look different, right? So being able to identify what your frequencies are at what times is important. So anyway, The simplest of this method is the short time Fourier transform, i.e. the spectrogram, in which one transforms windowed sections of the data to the frequency domain. So in other words, if I were to window this, I could say, rather than trying to do the Fourier transform of this whole thing, instead I'm going to do a Fourier transform here, and then I'm going to do a Fourier transform here, and I'm going to do a Fourier transform here, right? And so each of these is going to have a different looking frequency plot, but, you know, at a specific time, right? And so that's often a spectrogram is actually a piece of test equipment that you'll look at what the spectrum is doing, and it'll show you, it'll look kind of like a waterfall plot. So it's actually something like a, you would have frequency, you'd have time, and then you essentially have a third dimension that's color, right? So different colors, you know, you have essentially these time bins that you're looking at, and you know, so you'll have different colors over the course of this, and so those correspond to different amplitudes, right? So that's, and so you'll literally see this piece of test equipment that you could go and look at the what's going on around you. So that is a spectrogram, right? It's slicing up your signal into pieces of time and then looking at it. Time resolution is arrived at by centering the window function on the epoch of interest. So in other words, what segment of that spectrum you're looking at. And then sliding the window along a time axis. Thus, one may obtain a time frequency quote image that can serve as a useful tool in the analysis by delineating the frequency content of the signal as a function of time, much like a musical score denotes the individual tones in a piece as time progresses, right? Of course, if you look at written music, you know, you essentially have a, if you were to look at, I forget how many are on here, right? And so you'll have, say, like this, and then like this, and like this. And so this is now time, and these are different notes. So this is essentially frequency, right? As you go higher up the scale, you're going higher in frequency. So that's essentially what it's doing. It's plotting out what frequencies are around at a specific time, and you can have, you know, you might have multiple notes going on simultaneously. For example, you have a piano, right? Although I think it's usually a double bar. Anyway, it's been a long time since I've read music, but so you can have multiple frequencies going on. Anyway, that's essentially what a music scale is plotting. Okay. Although this method is easy to implement and indeed is an indispensable analytical tool, it fails to provide high time and frequency resolutions simultaneously. To localize some frequency component in time, one must choose a very short window, which will inevitably lead to poor frequency resolution upon Fourier transformation. So something to note. In order to get high frequency resolution, you need to be collecting information for a long period of time. In order to get in order to get very high time resolution, you need to be collecting at a lot of frequencies for a very short amount of time, right? So in other words, what do I mean by that? Yes, it is a Wagnerian-Wigner distribution. So what do I mean by that? Let's say I'm trying to capture a signal that has this in it, right? This frequency, and also has this frequency, right? If I want to capture this top frequency, I need to be listening essentially for enough time to capture actually at least half. You at least need to be able to capture half a wave essentially. Right? So I have to be looking for this amount of time to be able to check the frequency. Right? If I'm looking for a shorter amount of time, well, I might be able to identify this frequency, but I can't identify this frequency anymore. I'm inexact, right? My resolution between that and something close to it is off, right? I can't tell the difference between this here. From just looking at a very short time, I can't necessarily tell the difference between these two frequencies. In order to be able to tell what those frequencies are, I need to be listening for a longer period of time for them to have the opportunity to diverge effectively. But that means if I have a short spike in my signal, right? Let's say I have a short spike like this, I won't capture this spike because I'm listening over too long a period of time, right? My frequency resolution has improved, but my time resolution has decreased, right? I only know essentially the average of what's occurring over this time, right? My resolution is in these chunks. So I end up with this measurement problems where either I have good frequency resolution or I have good time resolution, but it's impossible for me to have both, right? So that's the problem with doing Fourier transforms using this sliding window method. My window is either long enough that I have good frequency resolution or short enough that I have good time resolution, but I can't get both. Notwithstanding its inherent resolution problems, the spectrogram has been successful in much data analysis, in part because most experimental data have temporal variations that are, quote, slow, right, in respect compared to how quickly I'm collecting the data. Or I'm sorry, the variation in frequency tends to be much slower than the frequency itself, right? So I can usually get away with that slop. That's okay. In some instances, most notable being human speech, the time variations of the frequency content can be sufficiently fast to render the spectrogram practically useless. Time-varying spectra were studied in the classical works of Gabor, Viel, Page, and Wigner. Their work was not motivated by improving the spectrogram, but by a desire to construct a joint time and frequency distribution of energy waveform-based general mathematical principles, right? So they were just looking at it from a broad mathematics standpoint. They were trying to solve this resolution problem. Wigner, of course, was concerned with constructing such a function for the quantum mechanical wave function, which, with its probabilistic interpretation, led naturally to the concept of a distribution function similar to those in probability theory. In the rest of this article, I shall describe Wigner class of distributions, and we'll show how they're related to two-dimensional ambiguity function, which is something we'll come into in a minute. I shall describe how the so-called interference terms can be filtered in the ambiguity function space to give examples of a distribution on synthetic data and present two examples. Okay. Most data sets are obtained by APL. So this guy was at Applied Physics Lab up in Maryland. Johns Hopkins Applied Physics Lab as APL usually. All right, so consider the waveform S of t, the instantaneous energy of the signal per unit time at time t is given by the magnitude squared of S of t. The intensity, per unit frequency is given by S of f squared, which is the standard Fourier translation relationship. In other words, what is it saying? Right? What this is saying is my signal in time is S of t, right? This is the time versus amplitude of the signal. That's what that is, right? This is the Fourier transform. This is the mathematical description of how you do a Fourier transform. right? So this is going to go from S as a function of time into S as a function of frequency, right? Because when I integrate from negative infinity to infinity, that integrates out the time dependence, and all that's left is the frequency dependence. So then by doing that, I've swapped over. This is, of course, to give a little background, remember how I said, right, S of F, right? So my signal's function frequency is sine of F1 plus, or A1, I guess, plus A2 sine F2. Actually, it's right. It's something like that, right? So it's this sum of an sine Fn and plus cosine, and right, there's also a cosine function in here too, right? Plus Bn cosine Fn, right? So it's this sum here, and there's a 1 over n, I think, right? I think it's 1 over n. Anyway, but this is just a simple sum, and then when you take that to n approaching infinity, this sum becomes an integral, right? Now I'm integrating from negative infinity to infinity. Ft, there's a t in there, right? It's 2 pi ft. But anyway, so now the sum, as n goes to infinity, this sum becomes an integral. And what they've done is they've taken this sine cosine and converted it just into a complex exponential. So if you notice, there's your imaginary term there. Of course, going e to I theta equals cos theta plus I sine theta, right? That's your conversion. So anyway, complex exponentials are a lot easier to work with than sines and cosines. So we go that route. All right. So this is a standard Fourier transform, as you would find it pretty much anywhere. Standard Fourier transform relationship. Percival's theorem then states that the total energy can be computed in the time or the frequency domain. So again, the total energy is how much energy is in your wave, and that's the magnitude squared of your wave integrated over all time, which is the same as the magnitude squared of your wave as a function of frequency integrated over all frequencies, which the same wave, right? You're just, whether you're looking at it in time space or frequency space, it's the same wave. It's just which way, which one you're integrating in. So they better be the same. You've literally, all you've done in doing the Fourier transform is gone from one variable to a different variable. You've just gone from time to frequency. So you'd better have the same physical properties of that wave, such as the energy that's actually in the wave. The fundamental goal then is to devise a joint function of time and frequency that represents the energy or intensity of the waveform per unit time, per unit frequency, right? That's ultimately what we want to do. We want to solve this problem where if you increase your time resolution, you're decreasing your frequency resolution by this other method, right? It's trying to solve that issue, that uncertainty part. Okay, this joint function, which we will denote by P of T and F, must necessarily follow the following marginal conditions. If we integrate it over time, that's got to be the same as the magnitude of the frequency squared. If we integrate it over frequency, it's got to be the magnitude of the time signal squared. Yeah, right. It's if you have a function of two variables, right? Two independent variables, and you integrate out one independent variable, then you're left with the other one, right? You've completely gotten rid of one, you're left with the other one. So the spectrogram is a time frequency distribution right? Because again, the spectrogram is frequency time, right? It looks kind of like that. And then intensity is a third dimension on this. The spectrogram is a time frequency distribution and is defined as follows, right? So my spectrogram function of frequency and time is the integral of s of tau. So tau, if you look here, tau is a dummy variable, right? It's going to be integrated away. And the window is describing the width of the window, essentially, right? So what you're doing is you're looking at some signal, right? And you're looking at it with some window that has a width tau, right? And you're taking that window over time, you're sliding it across, right? So this is going to be t, right? You're sliding it over t. You're taking this and you're just kind of shifting it down. I'm looking at what my frequency content is here. Then at a later time, right, that's now moved to here. And now I'm looking at the frequency content here, right? And that's how I'm building up this this plot. So that's what our window function, that's what it's described as. Usually it's something like, I mean, the simplest window function is just a step function, right? It's either 0 or 1. Usually the window function is more complicated than that, but just as an idea, right? That's typically what your window function can look like. That's what it can be. The Wigner distribution for a real waveform S of t, right? So some function of time, signal is a function of time, does satisfy the marginal properties, is a quadratic functional of the signal, and is defined as follows. So this is the definition of the Wigner function. Okay, so this is paralleling what the spectrogram, right? It's similar to the spectrogram in that it's a two-dimensional function of time and frequency, but it's going to be a little bit different, set up a little different, right? So we're integrating over tau again in the same way we were here. But now we have S tilde of t plus tau over 2 and S, this is the complex conjugate, S tilde of t minus tau over 2, where S tilde is a so-called analytic signal whose imaginary part is related to the original waveform by the Hilbert transform, thus this. This analytic, okay, so there's an easier way to do the analytic. Hold on. Give me a second. I know there is a better way. Analytic function. No, I want. What's it? Hilbert transform. All right. I remember there's an easier, that's a correct definition, but if I remember correctly, there's an easier to understand definition. Oh, let me pop this up so we can see what's going on. Understanding. There we go. Okay, and kablow. All right. Okay, so the Fourier transform real value blah 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 blah. Yep. So the continuous time analytic function. It's essentially you end up with a negative frequency component that's kind of mirrored across the DC axis, if you will, the f equals 0. Let's say that the magnitude spectrum of x of f is shown. We know that the signal x of t is a real valued signal, and its magnitude, the magnitude of x of f, is a symmetric instant infinity time domain, right? So, as mentioned, analytic signal can be formed by expressing the negative frequency components of the Fourier transform of the real value signal. That is, in frequency domain, the spectral content of a signal in the time domain is given by x for 0 for f equals 0, xf. All right, so so it's 0 for f is less than 0, right? Negative frequencies. This corresponding the corresponding spectrum of the resulting analytic signal is shown in figure 1b. One side of the spectrum corresponding to the analytic signal. Okay, so the analytic signal is just the positive frequency element of it. Am I doing that right? Since the spectrum of the analytic signal is one-sided, the analytic signal will be complex valued in the time domain. Hence, the analytic signal can be represented in terms of real and imaginary components in time. Right, so that's the other piece, right? In the same way how you have the problems with the resolution in time versus frequency, you're also going to have a problem with imaginary components. In order to fully express a real valued signal in time, you're going to have negative frequency components and vice versa, right? So if all of your frequency is positive value, you're going to end up with, right. So blah, 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 blah. Since the spectral content is preserved in the analytic signal, it turns out the real part of the analytic signal in time domain is essentially the original real valued signal itself. Then what makes up the imaginary part? Who is the companion to x of t? Imaginary part, who is the companion of x of t that occupies the imaginary part of the resulting analytic signal. Summarizing the equation, z of t is z real plus I z imaginary. So then if the real part is what we see, right, the actual signal, what's the imaginary part? So again, it's weird talking about the imaginary part of a real signal, but this is a mathematical, or this is a an artifact of using these mathematical tools. Okay. Because these mathematical tools are not restricted by the physical instances that we see, right? The physical instances are essentially subsets of the overall mathematical process. When you go through the mathematical process, you're going to end up with these extra terms that float around. So you have to take them into account when you're going to use this math as a tool to apply it to physics. It's interesting to note the Hilbert transform can be used to find the component function, the imaginary, right? So the frequency domain pair. Okay, so for the real value function, it's two. All right, so one-sided spectrum ZT is formed from the two-sided spectrum. Okay, the time domain approach using the Hilbert transform, right? Given by equation 4. That's not the guys. Okay, so this is the discrete time Fourier transform at this point. This is not very helpful. Give me the actual analytic solution, or the analytic equation. This is what we just saw. Yes, Hilbert transform. Yes, it's the imaginary component of it. Pull. We're getting sidetracked a little. In the interest of time, we're not going to go to it too much, but suffice it to say that what's happening is we are extending our signal into the imaginary through this here, right? We're integrating over this dummy variable chi, right? So we're taking S of, it's the same, this is our real valued equation, right? So we're taking our equation, we're integrating it in this form, right? 1 over pi times the integral, so that's your normalization constant, and t minus chi d chi. By integrating over all space for d chi, the dummy variable goes away, and you just end up with this expansion into the imaginary term. It's just another, the imaginary domain. It's just another term that's in there to make the analytic signal. Man, this is going longer than I thought it would. All right. The analytic signal. So, given that this is going longer than I thought it would, we're probably gonna just go to the end of this page, and we'll call it there for the first Saturday morning paper. Okay, so the analytic signal is used for several reasons. As is clear from definition, the Wigner distribution is a quadratic functional of the signal, and so it will in general exhibit interference between the negative and positive frequency components of the signal. So again, if you don't have a complex signal, you're going to end up with negative frequency components, right? That's the negative frequency side is the mathematical reflection of this extra imaginary real, in the time domain, you have this imaginary component that's reflected in a negative frequency component. That's just part of the mathematical structure of what's there, without real physical meaning, but it has mathematical meaning. And if you don't use the mathematical tools using these things, even though they don't have physical meaning, your physical answers are going to be wrong. So you have to use the mathematical tools correctly. Okay. However, the analytic signal is used in the computation. No negative frequencies are present, and hence no negative and positive frequency interference will persist. Yeah. So literally all that this analytic portion is doing is this is just canceling the negative frequency components. All it's doing. The entire purpose is to get rid of the negative frequency components. In addition, the analytic signal formulation guarantees that the first moment of the distribution is the instantaneous frequency, i.e. the time derivative of the signal phase function. As we shall see later, a practical algorithm for the computation of the Wigner distribution will have to rely on oversampling of the original waveform in order to avoid serious aliasing in the frequency domain, unless the analytic signal formulation is used, in which case no oversampling is required. So that's good, right? You want to avoid oversampling if you can. Oversampling means you have, if you're physically sampling a physical signal, you're limited by how many times you can actually sample what the signal is, the amplitude of the signals. So there's all these other issues that go on there. So if you can avoid the lower your sampling rate, the easier it is to implement in reality. So ideally you want a low sampling rate. So the following presents some properties of the Wigner distribution. Okay. An alternative definition of the Wigner distribution can be given in the frequency domain. So this is literally just the frequency version of it, right? We're now integrating over this other dummy variable instead of a time dummy variable, where S tilde of F denotes the Fourier transform of the analytic signal, right? So, of course, they need to be the same thing in the same way that you have to have the same energy. Whether you're in time or frequency domain, they have to be equivalent. These distributions have to be equivalent, right? They need to be the same thing. The marginal properties are satisfied, all right? So that's what we described over here, where if I integrate the entire Wigner distribution over time, I'll get I'll just have my signal in frequency. If I integrate it over frequency, I'll just have it in time because I've removed one of the variables by integrating it out. The Wigner distribution is time limited if the original waveform is time limited, and frequency limited if the original waveform is frequency limited. In order to have a time limited signal, you need an infinite frequency set. In order to have a frequency limited signal, you have to have an infinite time signal. These are these are the handoffs you're making, right? Back and forth between the two. These are mathematical results of what it means to have an oscillating signal. If f tilde of t is s1 times s2, right? So if I have two subcomponents of the signal, right? I've combined two signals together. Then the Wigner distribution of S is the Wigner distribution of the first one times the second one. Okay. Over an offset, integrated over the offset, right? So what I'm doing functionally is I'm sliding S1 over S2 in frequency, right? So I'm taking here's S1. Here's S2. I'm taking S2. I'm looking at the overlap as I move this across, right? I'm shifting it in frequency and I'm looking what the overlap is. And if I do this over the entire course of the signal, I will get this integral, right? The Wigner distribution and two-dimensional ambiguity function are Fourier transform pair. That's important. That's interesting. They come from very different areas, so that's good to know. The two-dimensional ambiguity function is commonly used in radar signal analysis as the most complete statement of the waveform's inherent performance, where it's looking at frequency resolution versus time resolution again, right? If I have a very long signal, I'm going to have very good, I'm sorry, it's spatial versus time resolution, not frequency versus time. If I have a very long signal, I can have really good spatial resolution. If I have a very short signal, I can have really good distance resolution. Or, I'm sorry, it's Doppler. Oh, man, I'm way off. The ambiguity function is Doppler resolution, Doppler versus distance. If I have a very long signal, I can have very fine Doppler resolution, so I can know how fast the target's moving. If I have a very fast signal, I have really poor Doppler resolution, but I have really good location resolution, right? I know exactly where this target is, but I don't know how fast it's moving, right? It's a similar relationship to what we were talking about before between frequency and time resolution. It's actually a result of the same thing, right? It reveals the range Doppler position of ambiguous responses and defines the range in Doppler resolution like this, which, if you notice, looks a hell of a lot like our Wigner distribution, right? The Fourier transform relationship is, this is just a standard, this is a two-dimensional Fourier transform. So if you remember, the other one was just one of these, but we're using a property of exponentials where we're saying e to the negative 2 pi I nu t times e to the negative 2 pi I ft, I guess it's f tau, equals e to the negative 2 pi I nu t or plus f tau, right? I'm just merging those exponentials that way. So it's literally just the same thing as the other Fourier transform, but doing it twice. The following diagram can be constructed where each arrow indicates a Fourier transformation of the indicated variable. Neat. So we can go, by doing a double Fourier transform, we can go back and forth between ambiguity function and Wigner distribution. Cool. All right. So I am going to call it here because I have other stuff I need to get done today, places I need to go today. So I'm sorry if I rushed that a little bit. On the next edition of Sunday Morning Papers, we will continue this paper. We'll finish this paper out. But you can see how these tools sort of fit together and how they're going back and forth between frequency and time. And it's how they're just different ways of how you're looking at a signal, right? and you're trying to understand different aspects of how that signal will function, and what as a result, what those signals are going to do when you're interacting with them in the real world. So yes, so we will continue this next Sunday. The next planned stream I am tentatively planning for Wednesday evening, and will be chapter 3 of The Hobbit. Unless something crops up, that is the plan, Wednesday evening. If you keep an eye on Discord, I will spam out a message in the Discord before I start doing that. And yeah, so otherwise, I hope you enjoy the rest of the remaining part of your weekend. I will see you at a minimum on Wednesday, and potentially before that for some gaming. But I like to do the gaming streams to sort of just pop-ups as I feel like hopping online and blowing up some tanks or something. Anyway, have a great weekend. I wish you all the best. If you are in a place that gets snow, enjoy the snow. Otherwise, I will see you in a few